Hi, this is lecture 15 and it's going to be the last lecture for this course. And we have come a long way since the beginning of this semester in January, and we had this big change after the midterm that we had to move everything online. And it's been it's been a long time. But here we are, the last lecture, and this is like the finish line for this course. So let's get started now. Today we have two topics to cover. The first one is Greens Theorem. The first one today is Greens Theorem. It's going to be related to line integrals. That is why in this first slide it's about the line integrals. I want to tell you something about the line integrals first before we go into the details with the Greens Theorem. So that is the first one, Greens Theorem. The second topic for today is surface integral, and that's going to be the end of this lecture. Surface integral. It's basically about how to find the surface area of the surface in 3D, but that is for the second half. Now let's get started with the line integrals, which is directly related to the Greens Theorem. All right. So line integrals, we have done this quite a few times in lecture 13 and lecture 14, and also in the homework too. So in these lectures and the homework, what we did is that we find the line integrals of vector field, and we have done 3 dimensions. Right? So we have this vector field in the space. This example that I brought up, this is 3D. So we find this line integrals of the vector field along a certain path. Along a certain path. And we are going to call this path a curve or something like that. Path or curve. It's possible to call it either way. Curve. And this is going to use the symbol C. So find line integral of f along C. That is what we did before. Well, I'm going to talk about this again today, but today I'm going to focus on just 2D, because the illustration that I had on the left hand side, this is a graph of x and y. So today I'm going to talk about this vector field of just x and y. Okay, so here on the graph we have this y-axis and x-axis, and as you can see, you see all these arrows and vectors everywhere in the space. So this is the representation of the vector field in 2D, and it's this big F of xy, and at each point you pick on the space you have different vectors, which means that the coefficient in front of the I component and j component is going to depend on x and y. So in front of I we have this function m, depends on the point you pick, first component, and then the next component j, you are going to have this function n, depends on the point you pick again, but this is for j component. And this is for this is the vector field in 2D. Alright, so when it comes to line integrals, it's not just about the vector field. We want to do some calculation of this field along some certain path, and this path has to start somewhere and end somewhere. So let's put 2 points in the space here. Have the first point here, I'm going to call it A. That is the starting point of the integration. And then we have this point B right here. That is the end of the integration. And as you know, when it comes to line integrals, you have to integrate along a path or a curve. It doesn't have to be a specific path like straight line from A to B. It can be any path you want. So here I'm going to pick one path that I like. It's going to be a little bit curvy, maybe around here, and then comes back to this. Okay, so this is the path I want, starting from A along the vector field and ends at B. So with this kind of information, let's put the simple C for this curve or the path that we had here. So line integrals for this is going to use this formula. It's going to be integration of this vector field xy. Alright, and we are going to do this along this curve C, and when it comes to this formula, it's going to look like this. This is the first form of the formula that we have. I'm going to call this first version, the most simple one, first version of the line integrals. Okay, once again, this is line integrals formula. Okay, formula for line integral. But there is a problem with this version because a lot of things can go on. We have this vector field in terms of x and y, and then we have this dr, which we don't know what it is. We can't just perform calculation along with f. And then we have this c, which is not specified what it is. So each things that we see here can be combined together. So that is why we did something more to this form in order to make it more manageable, in order to be able to continue with the calculation. Okay, the first thing that we do is that we find a variable. We find one variable that is going to be used across all these terms, and that is when we use t. So in order to make this manageable, I mean in terms of to go on when it comes to working on math, then we use t. Use t, the variable t, the time, to make formula easier to use. Okay, so how does t help with this? So let's start with this, with the first one. Okay, so the first thing that we did is that we have this c, the curve c, and at this point we don't know what it is, but then we have learned about how to create a line, a curve in the 3D space, and we make it equal to this vector function rt. That is the first thing we do. This rt is going to represent the curve in 3D. This rt thing, curve in 3D, and we learned about this before the midterm, long time ago. You can look it up again, but in the end, it's the idea of this rt becomes the curve that we want to travel from A to B. So what about we put this rt right here? So now C becomes rt, line in 3D, and it's going to have this I component and j component. This rt is going to be position vector, so it's going to represent the coordinate along the line, right? So in terms of the coefficient in front of I, it's going to change over time, and the coefficient in front of j, it's going to change over time too. And one thing you need to keep in mind, these two, this represent the xy coordinate in the Cartesian coordinate system. This AT, this is x coordinate, and BT here is y coordinate. And you notice that xy changes along this curve, right? And just the same here, as when t changes from the starting value to the end value, this big A and big B changes over time. AT and BT changes over time, over t. Alright, so that is the first step. Now C becomes r of t. So we have this common term of t right here. Now, when it comes to this path, this point A, what about we put the timestamp at this point A? Instead of using a location, we use the time. So at point A, we say that time at this point is t equal to small a. Same point, big A is the location, t equal to a is the timestamp starting at that point. So I'm gonna do the same thing with the big B out up here. This is timestamp with t equal to small b. All right. So the starting point and the end point becomes dependent on t. The curve now depends on t as well. The only thing that doesn't depend on t is this, f. At this point, f still depends on x and y. So we are going to do something to change this f, x, y to depend on t. So here we have this f, x, y, right? Up here we have this. Our job is to change this to make it depend on t. So we have this before, we have this f of x, y, but this is not going to go well with the variable t that we introduced. So we have to find a way to change this into vector field that depends on time. Okay, so in order to do this, all we need to do is to substitute a of t and b of t into x and y, because here we know that a is x coordinate, a equal to x, b here is y coordinate, which means that bt here is equal to y. So all we need to do is to substitute this coefficient in front of I and j from r into here. So this is what we do. This x here, we just substitute a of t. That represents the coordinate along the curve. And here, this is b of t. And in the end, you are going to get this f that depends on t. And with this kind of changing, starting from the curve right here, number 1, timestamp with the starting point and the end point, and also with this function itself, the vector field, we transformed the formula from the version number 1 to version number 2, and it looks like this. Version number 2, this is integration of same thing, f, but now f depends on t. Okay, and instead of using just dr, I use dr of t over dt, which is different from number 1, but if I dot this times this with dt, it's going to be it's basically the same thing, right? Try cancel this, it's same as form 1, but I'm going to leave it like this for now. Alright, and I group this together. Okay, and instead of having this symbol c for the curve, I use the timestamp starting from t equal to a starting point and ends at t equal to b. Now everything is in terms of time of t, and that means that in terms of calculation, it's easy to carry on. So this is version number 2. Right. Okay, so we have this version number 2, and this is easy to do calculation. Calculation on. Okay, now we have seen 1 and 2. 1 is the most basic, and then 2 is something we use in examples and homework. But today I'm going to show you another form that you might run into, maybe in the book or maybe in some other notes. So let's take a look at the form number 3. Well, I need more space, so what about I erase some of the stuff up here at the top? this has to go along with this. Well, by now you know what the vector field is. Okay. Now it's going to be about the third form that you might see later in other courses or something. So let's start with the form 1, and let's take a look here. This form 1, f, right here, f of xy. This is equal to what? Something that I already erased. This is m of I. Well, m depends on x and y too, but this is the short form, plus n of j. That's what we have for this thing. But now, differential r. This is differential displacement in the direction of the integration. So dr right here, let's add something. Dr right here, it's equal to differential in the I component in x direction plus the differential in j component in y direction, dyj. Think of this dr like this vector, and then you separate it into two components, j component and I component. Alright, this is dx, this is dy, and the original is dr. Okay, so we have this, and as you can see in the first form, this is the dot product of these two. So let's find that. Dot product of these two. It's going to be equal to the product of the component I, so that is m dx. I need to change color. So product of this dx and m, so I get m dx plus the product of the next component, which is the j component, dy and n, so this is n dy, and the rest is the same, this integration at the front along the curve. So sometimes you see the line integration in this form. Don't worry, don't get confused about this. It's the same thing. It's the same as the form number 1. So this is form number 3, something you might run into. Another form of line integral. Just keep in mind that it's the same formula, except that you do some modification, like the steps that I just showed you, and you get a new form. But in terms of calculation, it always comes to this form number 2. Okay? Alright, so that is what we did before. Now, today we are going to learn about form number 4. It's going to be a special one, and it requires some special conditions. And let's take a look here. This form number 4, it's going to be related to Greens Theorem. So what about I move the form number 1 right here. So form number 1, we have this. We have the line integral of the vector field f of x, y along a certain curve, and this has to be done with respect to the differential displacement, the dr. So that is form number 1. Okay, form number 1. And I bring this because this is related to Greens Theorem. So let's take a look at what conditions can we use the Greens Theorem. Alright, so we have this form number 1, and let's add more conditions to this. If in this line integral, the line integral, the path that we perform is a closed loop. Alright, the first one is closed loop. Path is closed loop. What does it mean to be closed loop? Alright, let's take a look here. before we had this point A, alright, and we had this point B, and we performed the line integral along this vector field, maybe something like this, along this curve, and ends at here. And we have this timestamp starting at t equal to small a and t equal to small b, and we end at this point B. This kind of path is not a loop because you start somewhere and you end somewhere else. This is not a loop. It's going to be a loop if your path comes back to the original location. What if you continue this? What about you erase the erase this point B, and you create something like this, a path that comes back to the original point. So at this point, it's not just A, it's also B too, and B happens at t equal to B, but it turns out that the location A and location B is the same. Alright, this kind of thing, this path is closed loop. So C here is closed loop. What it means is that it comes back to original location. And there is one more thing about this closed loop, about this condition. It has to be simple. Alright, so what does it mean to be simple? Let's take a look at the picture on the left hand side at the lower part. Take a look at this. Simple is something like this. First one, number 2 is simple, and number 3 not simple. Why? Because in number 3 the path crosses each other, crosses along the way. So if you notice some crossing like this, this is not something like this. Crossing of path, then not simple. So we don't consider this this not simple case. We only consider 1 and 2, just simple one. So closed loop, and it has to be simple. This is the condition that we need. Alright, number 2, the condition that we have to meet in order to use the Greens theorem is that this path, we have this moving along the curve. Alright, so path circulate in counterclockwise direction. I would say circulate. Okay, circulate in counterclockwise direction. As you have seen from above, when it comes to integrating along the curve, we have timestamp. We're starting from this point, and then we move along this curve according to the time and ends at here. So if you look at this, if you do the same thing, it's gonna look like this. Starting from A along this curve and comes back to the original location. Alright, and you look at this and you can see that, hey, this is circulating in counterclockwise direction, right, on XY plane. Counterclockwise direction on XY plane. So this is good. So looking at this this graph on the left hand side, you see a closed loop. Alright, closed loop. And this loop, the path circulate in counterclockwise direction. So we meet 2 conditions here. So we are allowed to use the Greens theorem for this kind of situation. Let me use something. Let me put this again. Integration of f xy dot dr. That is the first form along a curve. But now we have two more conditions. Path is closed loop. This condition number one can be I would say that we can present it in terms of symbol. We can use this to show that this is a path that is a closed loop, this circle. So when you see this, you have to know right away this is about integrating along a path that comes back to the original location. Alright, this thing, closed loop. Okay, and also we have to add some another thing when it comes to the circulation in counterclockwise, so we can use this symbol to show that, hey, this is not just a closed loop. This integration is going to move in this direction too. So with this line integral that is closed loop and counterclockwise direction, it's going to be equal to something different. And here is the formula. It's going to be the double integral, something we have done before, of n with respect to x minus m with respect to y dx dy. You might ask, what is n, what is m? That is the component for the vector field. So let's put it here. F xy equal to m xy I plus n xy j. So instead of having to perform the line integral, now you just had to perform the double integrals, which you have done before. And I mean, I don't know about you, but to me double integral is easier to do than the line integrals. So we have this formula. Alright, so let's take a look at this formula again. So we have this nx right here. This is partial diff of this n component for the j component for the vector field with respect to x, and this is the differentiation of m, the x component of vector field with respect to y. Alright, and we perform this double integration, and as you remember, double integration has to be performed on a domain region. So this has to have a domain region R. And this R represents the R that is enclosed by this path. This is the R that we refer to in the formula. Okay, as long as you know the shape of this loop, you can perform the double integration. So that's what you just see is the Greens theorem. Alright. What is special about this? So if you have this condition met, it means that you don't have to perform line integrals. All you need to do is just to perform the easier double integrals. When all conditions are met, this is the key point, perform double integral instead of line integral. I mean, based on my experience, double integrals easier to do than line integrals. Well, you might not believe me, so let's take a look at this example 1, and we are going to compare between the traditional way of line integrals and the one that we use Greens theorem to perform the integration. Okay, so next example, number 1, we are going to use two methods. The first method is going to be just regular line integral, and then we are going to try the Greens theorem and to see whether they come out to be equal and to see whether it's easier like I said. Okay. Alright, so what do we have here? We have this vector field F, alright, we have a mistake here. This is just x and y, so just cross z out. So we have this vector field in 2D. Alright, and we have this path, this cosine t I and sine t j, and we need to find line integral of f xy along r of t. Okay, so let's try the way that we had done before in lecture 13 and lecture 14. So what do we have here? We have this r of t equal to cosine t I plus sine t j. At this point, we know that this is the equation for the curve. All right, this is C, which is the curve or the path, which means that the component in front of I and j, these coefficients represents the x coordinate and y coordinate. So at this point, we know that, hey, x coordinate that we are interested in along this path is going to be equal to cosine t, and the y coordinate is going to be equal to sine t, right? X here and y here. This is position vector. Now with this information, we can transform fxy that we had before to be f that depends on t. Before we had this x minus y I plus xj. But now we have more information of x and y. Substitute that in. So what do we have here? We have x, which is equal to cosine t, minus y equal to sine t. First component I, all right, plus x here equal to cosine t j. All right, so this is f as a function of time. Okay, and in order to use the second form, let's take a look at the formula. The second form looks like this. Integration of f that depends on t dot dr of t by t. Integrate this with respect to t, starting from time equal to a and ends at time equal to b. And this reminds me that I forgot to put one more information about this example. This integration has to is to be done from t. Let's add this t starting from 0 and ends at 2 pi. We need to know the time. Without this, we cannot go on with the integration. Okay, so a and b, we know that this is a 0 and b equal to 2 pi. Sorry about this missing information. It's supposed to be given at the beginning. All right. Okay, so what we are missing here is this dr by dt. So let's find that. dr of t by dt. What we need to do is to diff this. To diff this r with respect to t. So I just diff component by component. What do I get here? Diff cosine t, I get minus sine t of the first component, and then I diff sine t right here. With respect to time, I get cosine t j. Alright, so I can find f of t dot dr of t by dt. That is the sum of the product of each component. So starting with the first component, product of that becomes minus sine t cosine t, and then plus sine t square. Alright, and then plus the product for the next component, that is j component. The product of that, we have plus cosine t square. Now in the end, this is equal to, well, what about I move to here? Integration. Okay, what about this cosine square plus sine square? This is going to be equal to 1. So what you see here, this is 1 minus sine t cosine t. But from my experience, product of sine and cosine, it's going to be a little bit tricky to perform integration on. So what about I change this into just one term, and this is equal to 1 minus sine of 2t using the trigonometry property. So you get sine 2t over 2. Alright, this is going to be the thing that we put into here. Alright, so we are going to perform the integration. Oh, okay, we have enough space. Okay, we are going to perform the integration starting from time equal to 0. The information that we had from the problem ends at time equal to 2 pi. Alright, and ft.dr by dt we have down here 1 minus sine of 2t over 2. Integrate this with respect to time. Right, and this is going to be equal to, alright, this is going to be equal to t, and this is going to be equal to minus plus cosine 2t, 2 still there, and then with the chain rule backward, so we have one more term right here, and we have to evaluate this at two value of time, 0 and 2 pi. Alright, 2 pi goes in, we have 2 pi right here, plus cosine of 4 pi, that is going to be equal to 1, so this is 1 over 4. Minus, now 0 goes in. 0 goes in, so I have this t equal to 0, and then plus cosine of 0, that is going to be 1, and divided by 4. So plus 1 over 4. And you can see that this 1 over 4 cancel with this. So in the end, you have this 2 pi as the answer for this line integration. So it's this integration of this vector field along this curve, and we have this time for the starting time and the end time right here. The information we had, 3 things: vector field, path, and also the time. Okay, now that is method 1. Let's try the Greens Theorem. Whether we first we have to check whether we can use it, and if we can, let's see whether the answer is going to come out the same, and also see whether it's easier or faster to use that. Okay, now same example, but let's try a different method. Okay, let's take a look here. Same vector field, same path, and also same time. Starting from t equal to 0 and t equal to 2 pi. But if it happens that before you start doing this example, you draw the graph. Alright, so let's assume that you draw this graph before starting, and you draw this path r of t, and you can see that starting from t equal to 0, that's going to be this point 1 right here, and when time increases, when time passes, is going to circulate. This is pi over 2, and then when time equal to pi, it's going to get to here, and then when time equal to 3 pi over 2 gets to here, and then when it comes to time equal to 2 pi right here. So this is r of t, time equal to 0. At this point, time equal to pi over 2. At this point, time equal to pi. Well, you get the idea, and comes back to here at the original place. This time equal to 2 pi. Alright, so we want to find this. The integration, line integration of f xy along this curve C, and the formula for the first form is this. But now we can see that, hey, looking at this curve that we just drew, this is a circle. Circle of radius equal to 1, and it's definitely a closed loop. Closed loop. Is it simple? Yes, because you don't see the crossing of the line. And also simple. No crossing. Which means that in this case, we have the condition number 1 for Greens theorem met. This is closed loop. Right here. Well, what about I use the green color? Closed loop. So condition number 1, closed loop. Check. We have that here. Good. Now let's see if this circulation of the moving of the path is counterclockwise, just like we had before. So here, starting at time equal to 0 right here, and it's going to move along this direction, right? Along this direction, and comes back to the original place. So as you can see here, this is counterclockwise. Alright, so condition number 2, counterclockwise direction. So we put this sign right here to say that this is not just a closed loop. In terms of moving along the path, we move in counterclockwise direction. So we can use Greens theorem here. Alright, so if we can use Greens theorem, we don't have to perform the line integrals. Instead, we just we can just perform the double integral, right, of the m with respect to x. Well, what about I bring the formula here? Oh, sorry, n with respect to x minus m with respect to y dx dy over the region, this region R. Now let's find n and m. This is n right here, this is n, and this is m. Okay, and this is going to be equal to the double integrals. N, which is x, differentiate x with respect to x, I get 1. Now m is x minus y. Diff that with respect to y, I get minus 1. Dx dy. Here it combines to be 2. Since this is constant, I take this out. This is equal to 2, and I take it out right here. So this is going to be 2 double integral. Alright, 2 comes out here, the double integral over the region R of just 1 inside dx dy. So here this is dA. If you recall what we did in the double integrals, this is the differential area, and now we perform the double integrals on this area. The whole thing here, this is going to be the area of R, and in this case this is equal to pi r squared. This is a circle, right? And r is equal to 1, so this is equal to pi. So this whole chunk equal to pi, which means that in the end we have this equal to 2 pi. As you can see, method 1 perform the line integrals along this this curve, and we do it in a traditional way, move from starting point to the end point, and we get this 2 pi in method 1. And in method 2 we test for the conditions for the Greens theorem. We see that, hey, this is closed loop, and we also see that this is counterclockwise direction, so we use Greens theorem, and it becomes just the double integrals. And in terms of calculation, I think this is easier, and as you can see here, just a few lines and you get the same result, 2 pi, and this is same as method 1. Number 1. Just keep in mind that it's not always that you can use the Greens theorem. It has to have these two conditions, 1 and 2, right? But maybe before you start doing the problems, you can just check the path, whether it's close or not, and that might save you some time because you might be able to apply the Greens theorem. Okay, now let's take a look here. One more example about the Greens theorem. So I give you this this vector field right here, f y squared I plus xyj, and I ask you to find the line integrals. Find the line integral of this f along a curve, right, where this curve is a square cut from the first quadrant, where this c is square cut from the first quadrant by using lines x equal to 1 and y equal to 1. By lines x equal to 1 and y equal to 1. So what is this path? So let's find out. So let's draw this. So we have this y-axis and x-axis. So this c is going to be a square, right? This is something we know, and it's going to rely on the line x equal to 1 and y equal to 1. X equal to 1 right here, and y equal to 1 right here. And this curve is going to be a square and cut from the first quadrant. So as you can see here, it's going to look like this. Ooh. Okay, I made a mistake. I need y-axis back. Alright, okay. So a square, first quadrant, y equal to 1, x equal to 1, it's going to look like this. So from the look of this, you know right away this is closed loop. And then the information doesn't stop here, and it says that circulation of the path is clockwise. Is clockwise. Which means that we are going to get something like this. Okay, so closed loop, we have that number 1 ready to be used in Greens theorem, but it turns out that in terms of circulation we have this clockwise. So condition number 2 is not met by what we agreed on before. So condition number 2 is counterclockwise, and we can see that, hey, this is not true here. Alright, what are we going to do here? So let's try to bring the formula back to this example. So here, before we had this formula, integration of a closed loop, and it has to be counterclockwise of f dot dr over a closed loop, a curve that is closed loop. And if we have these conditions, closed loop and counterclockwise, we can use the Greens Theorem, and it's going to be the double integral over this region R, right, of f of n with respect to x minus m with respect to y dx dy. But it turns out that in this case, the circulation is clockwise, not the same as has been stated in the theorem. All right. So what are we going to do here? This is not true in our case here. It turns out in this case, the circulation is this. This is clockwise. But the good news is we can just adjust something about this formula to fit this opposite direction of circulation. So when the circulation is clockwise, the formula is going to be a little bit different. All we need to do is to put the minus sign in front of the double integration. And this is the formula for the clockwise circulation. All right, this is Greens Theorem. Greens Theorem. And this is clockwise. Well, let's try using this to find the answer for this problem. So we have this f up here, and this is m, and this is n. So using this formula, closed loop, clockwise along this curve, f dot dr is going to be equal to minus double integration over this region R, which is a square. N with respect to x, so I look at this n. Diff this with respect to x, I get y. Minus diff m with respect to y, I look at this. I diff this with respect to y, I get 2y. Right? And then this is double integration with respect to x and with respect to y. Now you can see that inside here this becomes minus y. Minus y, this chunk, minus y, it's going to cancel with the minus in front. So in the end, this is equal to integration of y dx dy over this region R. And now we have to perform these double integrals. Let's recall what we did before when we learned about the double integrals. We need to sweep the x variable first. So as you can see, we sweep the x variable like what? Starting from x equal to 0 to x equal to 1. X equal to 0 to x equal to 1. So the starting point for the x sweeping is x equal to 0. Ends at x equal to 1. And for y, that is the whole range starting from 0 to 1. Y 0 to 1. Okay, now that's going to be equal to xy, right? Diff the first time with respect to x, I get xy, and I need to evaluate at x equal to 0 and y. And still, I need to integrate this with respect to y, starting from y equal to 0 and ends at y equal to 1. Now this is equal to integration of y minus 0, starting from 0 to 1 with respect to y. This is equal to y squared over 2, 0 to 1. And of course, this comes out to be 1 over 2. Alright, so if you see some situation like this, when you see a closed loop, think of Greens Theorem. Don't use the regular line integrals. Otherwise, it's going to be much more complex. So let's imagine if you don't know about Greens theorem, how are you going to perform this line integral? You have to do it 4 times. You have to specify this curve. The first chunk is this. So you are going to go from starting point along this direction. So you have to define this first curve, r of t, number 1, and then you perform the line integral along this one section. And after that, you have to perform another line integral along this section. And this section requires you to use different r. That's rt number 2, different from the first one. And after that, you have to perform the line integral again on the third section. And this is different r as well. And it's going to be the same for the last section, number 4, r number 4. If you didn't know about the Greens theorem, that is the only way. Starting from first section right here, then move to second section, then third section, and then the fourth section. Alright, so as you can see here, when you know about this trick, the calculation is just 1 page, like just a few lines. This is going to be much more time saving than having to go through all these 4 sections of line integrals. Okay, so keep that in mind. When you see closed loop, think of the Greens theorem. Alright, so this is the same example as this one, but let me tell you about something. When it comes to the closed loop, before we had this square that start from 0 to y equal to 1 and then move along x-axis and come back to the original place. This loop doesn't have to be a square, doesn't have to be a circle. It can be something else too. What if this same example has this loop instead, this path? So also 1 here and 1 here, but the path in this case is this triangle. What are you going to do? Alright, so starting from this point and circulate just like before in a clockwise direction. So this point is 1, 1. Alright, so don't get confused about this. We need to check the conditions. So check, is this a closed loop? And the next thing we need to check is, hey, is this counterclockwise or clockwise? Now that we know the version for the clockwise, it can go. We can perform this on either direction, C or C direction. And as you can see here, we have these 2 conditions met in this example, 1 and 2. This is closed loop, definitely closed loop and simple. And it turns out in this case we have clockwise circulation. So we are going to use the this formula. Alright, so let's bring it here. Perform the line integrals of the closed loop in the clockwise direction over a curve of vector field xy. Alright, it's going to be equal to minus double integral of partial diff of n with respect to x minus partial diff of m with respect to y, and perform this double integration with respect to x and then respect to y over this region. Same formula, but now we have different loop. Before we have a square, but now we have this triangle loop, triangular loop. Now, I should say triangle. So what would be the difference here? Before we do this, before we had the square, we say that x sweep from, this is from the previous slide, x sweep from 0 to 1 and y sweep from 0 to 1. But here is not the case. Alright, we have to find out the starting point of x and end points of x in this case. So I want you to recall what you have done before. You did this. Alright, as you can see here, we are going to perform the double integration with respect to x, which means that we are going to sweep the x variable first. So as you can see here, we sweep the x variable from this line to this line, this line to this line. So in this case, we have the left line and the right line. The left line, this is y equal to x, and the right one, this is x equal to 1. So x is going to start sweeping from the left function to the right function. So here it's going to be starting sweeping from x equal to y. Ends at, okay, what about I put this in the next line. This is region R. In this case, this region R is going to be the double integration. Same thing, nx minus my dx dy. X starting from the left hand function, which is x equal to y, and ends at x equal to 1. Alright, and now for y, that is the whole range starting from y equal to 0 and ends at y equal to 1. Y equal to 0 and y equal to 1. This is old stuff. So if you forget about this, you can look it up from the maybe lecture 12, maybe 11. I'm not sure about that, but you get my point. So watch out about this. Okay, now that is it for the Greens theorem. So to summarize about this, it all comes back to these conditions: closed loop, and then counterclockwise or clockwise circulation. If you have these two conditions, use Greens theorem. It's going to be much faster. Alright, now next topic, surface integrals. It's going to be the last topic for this course. So let's talk about, I'm going to note some key points about the surface integrals, about what it is. Alright, so when it comes to surface integrals, this is finding the surface area. It's about finding the surface area. Like you see the surface here in the space right here, and then you want to find this area. Of course, since this is curvy, it's not going to be just a regular rectangle. It's going to have an area that is basically more than that, more than the just regular rectangle. So this is about finding the area of surface in the 3D space. A of surface, any surface in 3D space. Well, the version that I told you here might be short ones because I want to keep this as compact and easiest to understand as possible. So if you want more details about the proof of all the formulas that I showed here, you might need to look up the book. But here, this is the compact version, and you can just start using the formula right away. Alright, so first thing, finding the area. Now the next thing that you need to know about the surface integral is that when it comes to this, you have to always look for the integration domain. always look for integration domain. And the symbol for this integration domain is R. So when it comes to finding this A, you always look for this R. So what is this R to you? So if it's up to me, I'm going to see this R as the shadow of this surface A onto a certain plane. Alright, so you can make a note here. This R is the shadow or projection of the surface S of S on a plane. And usually when we work on this surface thing, it's the plane that we look for this shadow, it's going to be most of the time, mostly XY plane. It's like we shine the light from the above, you know, like this, from the Z direction, and we get this this projection on the X and Y plane, something like that. We are going to run into situation like this mostly. Okay, so so keep this in mind. This always look for R. This is important when it comes to the integration, and keep in mind that this R is usually on the XY plane. Alright, what do you need in order to find this surface area? Now let's take a look at the some formulas. The first thing you need to define the surface in the space. So look for this F X Y Z equal to C. This is going to be the first thing you need in order to calculate the surface integrals. This represents the surface in 3D space. This is going to be equation for surface in 3D space. Like here, for this S, you always have to find this equation fxyz equal to c, and when you have this, you can use this formula. I'm going to give you this formula right away. Let's not spend too much time on the proving. If you need to know how this this formula comes into play here, you have to look up in the book, and if you don't understand that, you can ask me. But for now, let's take a look at the formula and let's use it. Right. So the surface area. Okay, I need some space. Okay. The surface area that we want, it can comes from the surface integrals. Is going to be equal to the double integrals over the integration domain R. And that is why I ask you to always look for R. Find out the shape of R, because you need it when you perform the double integration. Now, inside the double integration, you have to find the gradient of f xyz and find the absolute value of that, divided by the absolute value of the gradient of f xyz dot p hat, also absolute value here, and then you perform this double integration over the integration domain. Okay, so this is it. This is the formula to find the surface area or the surface integrals. Now you might wonder, what is this P? Alright, so let's make a note here. P, this P hat is unit vector. This is unit vector that is orthogonal to R. All right, some of you might still don't know, still don't know what this P is. So think of this. This R is on XY plane, right? So if P is going to be something that is orthogonal to R, it's going to look like this. Orthogonal to this R. This R is on XY plane. And this tells us that this P is going to be this vector K, right? Alright, so this K orthogonal to the domain region. Alright, so we have all the information that is needed to perform the calculations. Once again, this formula is given to you directly here. I didn't prove it. If you need a proof, we can always look it up. Okay, let's use this formula to find the surface area of some examples here. Alright, so here we have this sort of like a bowl or a glass, whatever you think it is. So we are going to find the area of this. So first, let's take a look at this. This is a paraboloid, and it has this equation that describes this surface. And this paraboloid is cut off from the top by the plane z equal to 4. So as you can see here, this is cut right here. It doesn't go up anymore. So at this point, it got cut by z equal to 4. And now we want to know the area of this surface. All right, I tell you, the first thing we need to find is to find this f x y z. That represents the surface, this surface in 3D space. And as you can see here, f x y z is equal to this equation, x squared plus y squared minus z equal to 0. In this case, this 0 is the c in the formula that we have here. It can be some other values, but we have this ready. This is the f that we want. Alright, now we have this shape right here. This is R. Down here, this is the shadow of this ball. And as you can see here, x, y, this shadow is on xy plane, which means that P that we are going to use here, vector P, is equal to vector K. Alright, now let's do the calculation. Now first, let's try to find the gradient of f. Gradient of f is going to be equal to the partial diff of f with respect to x, the first component, plus partial diff of f with respect to y, second component, plus partial diff of f with respect to z, last component. And as you can see here, this is equal to 2xi plus 2yj minus k. And now we need to find, oh, by the way, the formula is this: double integration over the domain region of the absolute value of f, gradient of f, and the absolute of gradient of f dot p, and over this region. Now let's find the absolute value of gradient of f. Absolute value of gradient of f is going to be equal to the square root of 2x squared, each component square, and combine them together, 2y squared plus minus 1 squared. And this is going to be equal to 4x squared plus 4y squared plus 1. Okay, so that is the first term we need for the numerator here. Now we need this gradient of f dot p. So we need to find this dot p, which is k hat, and you can see here that gradient of f dot p is going to be equal to minus 1, right? And then we put this absolute value, it's going to come out to be just 1. Okay, so now we have everything we need in order to perform the double integrals. So let's put everything together. So we have this double integrals of the domain region R. Okay, and we have this absolute value of gradient of f, that is the square root of 4x squared plus 4y squared plus 1 divided by 1, and this has to be performed with respect to differential area. Now we need to do this, but before you continue, I want you to pay attention to this domain region R. As you can see here, this domain region R, the shape of this is a circle. R is a circle, which means that if you use the Cartesian coordinate to perform the double integration, it's going to be hard to do. Alright? When the domain region is a circle, it means that using polar coordinate is the way to go. So instead of staying with x and y, we are going to move to r and theta here. Alright, so here this is what we have. Double integration of r, that is a circle, and we have this square root of 4x squared plus 4y squared plus 1 and dA. Imagine having to integrate this with respect to x and respect to y. That is not going to be fun. So let's change this into a polar form. Okay. Alright, so in polar form, dA is going to be equal to r dr d theta. We have done this before, so if you don't remember why this is equal to r dr d theta, always look back the previous lecture. Now, this can be transformed into r and theta, right? So we can combine this. We know that r squared is going to be equal to x squared plus y squared, which means that this chunk is going to be equal to 4r squared. Now what do we have here? We have this double integration over this circle. Alright, this domain region of square root of 4r squared plus 1 r dr d theta. We are talking about this region here. Now we have to specify the range for the radius and the theta. Now let's take this out. In this double integration, we have to perform the double integration, the integration with respect to r first. So we can see that r have to sweep from r equal to 0 to r equal to 1. So r sweep from r equal to 0 to r equal to 1, and theta then needs to sweep from theta equal to 0 all the way through to and come back to here, starting from 0 and comes back to 2 pi when it comes to the angle. So theta starting from 0 and ends at 2 pi. After this is just double integration that we used to do. So let's do it for practice. Okay, so what about we start doing the integration here? Alright, so as you can see here, we have this square root of something inside. If we perform the integration right away, it might be hard to do, so why don't we use the first technique that we can think of to make things simpler. That is the substitution. So I'm going to make this equal to u. U equal to 4r squared plus 1, right? Which means that du by dr equal to 8r, and dr is going to be equal to du divided by 8r. Now perform the integration here. 0 to 2 pi, r equal to 0 to 1, this is square root of u. Now r just the same, and then we have dr equal to du divided by 8r. du divided by 8r, and we still have this d theta here. Right, it turns out that we got lucky. Here r cancel each other. Alright. Okay, so now let's continue. This is u to the power of 1 over 2, so I'm going to integrate that. This becomes u to the power of 3 over 2, and we still have 8 down here. And when we integrate, don't forget to divide this by the factor that we have, that is 3 over 2, so this becomes 2 over 3. Double integration, 0 to 1, that is r, and theta 0 to 2 pi. D theta, evaluate this at, oh my god, I made a mistake, I'm sorry. We have integrated the first time, so this has to go away. So we evaluate this at r equal to 0 and r equal to 1, and one more integration after that. And as you can see here, this is integration with, we have to evaluate with r value, but we have u in the integration, so let's move r back to its place. So we have this integration theta from 0 to 2 pi. Now this is 2 over, we can cancel this, 2 and 8 becomes 4. So this is 1 over 12. And we have u is going to be equal to 4r squared plus 1. Now this is square root of this, and with this, what about this is messy, so what about I keep it just the same as before, 3 over 2. 3 over 2. Evaluate this at r equal to 0 and r equal to 1. Right? So r goes in, and d theta. So r equal to 1 goes in, this becomes 4, and let me check, sorry. Alright, there is something wrong. Oh, this is silly mistake. I am sorry. This right here 1, as you can see, this is a circle of radius 2. Circle of radius equal to 2. So this, when I sweep this, this is not 0 to 1. It has to be 0 to 2 right here. That is why number is off. Okay, so I need to evaluate at r sweeping from 0 to 2. Alright, so this has to be 2, and this has to be 2. Sorry about that. So 2 goes in, this becomes 4 and 16, so this is 17 to the power of 3 over 2. Minus 0 goes in, that is going to be 1. And I need to integrate this 0 to 2 pi. And I take this 1 over 12 outside. Alright, integrate this with respect to theta. And as you can see here, this inside is all numbers, so I don't need to worry about worry about these terms, I can just take it out. So it's going to be equal to this 17 to the power of 3 over 2 minus 1 over 12, and integration 0 to 2 pi of just 1 inside with respect to theta. Right, so this 17 to the power of 3 over 2 is going to be equal to 17 square root of 17 minus 1 divided by 12, and the integration comes out to be 2 pi, right? Or you can say 2 pi minus 0. So in the end, you have this 17 square root of 17 minus 1 times pi over 6. And that is the answer. That is the area of this surface. Okay, once again, sorry about this little mistake here. I used 1 before, but actually if you look at the equation here, this is a circle of radius 2. I mixed it up with the previous example, which is the circle of radius 1 right here. Alright, so in this case it's not 1, it's 2. So don't do mistakes like this. Okay, so that is the first example when it comes to surface integration. Let's take a look at one more and we call it a day. Okay, example 2. It's going to be similar to the previous one, but let's take a look anyway. Now we need to find the area of the okay. Alright, there is a typo right here. This is from the previous example, so let's take a look at this one. Okay, so we have this surface. It's just a part of the sphere. So we have this sphere, x squared plus y squared plus z squared equal to 2. So as you can see here, this is a sphere of radius equal to 2, right? And then we didn't just want to find the surface of the whole sphere. We just want to find the surface of just part of it. And this part is cut off by a cylinder of x squared plus y squared equal to 1. This. So we have this sphere, and then it got cut off by this cylinder. It's like we have this sphere, and then we put a tube all the way through from the top, and then what comes out is this surface, just this part. This is like the top of the sphere. Top of sphere. So you can make a note here, this is about the top of the sphere. Cut off by a circle, x squared plus y squared equal to 1. A circle of radius 1 just cut through from the top, and you get this sort of like a cap or upside down bowl. Think of maybe a coconut or something, and then you crack it open, and the top of that is the kind of shape we are looking at here. So alright, so this is the information we have. So we are going to start to perform the integration to find the surface area of this. We want to find the surface area of this. So the first thing is to find the equation for the surface that we are interested in. So that is f, x, y, and z. Okay, and it's going to be equal to this x squared plus y squared plus z squared, and that's equal to 2. Alright, so the equation that we are looking for is this. In this case, c is equal to 2, but the example before this one, c equal to 0, so it's okay. All we need is the xyz part. So here, this is the equation for the surface. So don't worry about this c equal to 2, and in this case, for this one c equal to 0. That is okay, doesn't matter. We are interested in just f. Okay, now we have this f ready. What we need to do is to find the gradient of f, because from the formula we need that. Gradient of f is going to be equal to the partial diff of f with respect to x, that is 2x, that is for the first component, and partial diff of f with respect to y for the next component, that is 2y, and then partial diff of f with respect to z, that is 2z, and this is the last component k. Alright, so this is a gradient of f, but then we need to find the size of this, sine of this gradient of f. It's going to be equal to the square root of this first component square plus second component square, last component square, right? And it's going to be equal to 4 x squared plus y squared plus z squared. Well, we can keep it like this, but it turns out that we know that on this surface we have this relationship. X squared plus y squared plus z squared always have to be equal to 2. That is the radius of this sphere. So it turns out that we got lucky. This term equal to 2. It's coming from what we have from the problem. This is different from the example up here. The example up here, we leave xy in because we can't substitute to get rid of it. As you can see here, still have x and y here, and we have to go on with this. But for this case, it turns out that we can simplify this even further, right? So in this case, we have the result of this equal to 2 square root of 2, right? Just one constant. Now, okay, and then we need to find gradient of f dot p. P here, once again, we are looking at the shadow or projection that looks like this. Let's take a look here. This is the projection on the xy plane, right? Projection of this cap at the top of the sphere. This is r, and r is on xy plane, which means that vector p has to be orthogonal to xy plane, and that has to be vector k. So gradient f dot p is going to be this dot with vector p, and it comes out to be equal to 2z. 2z, and we want the absolute value. So absolute value of 2z, and when you look at the graph up here, z is always positive, so you don't have to worry about this absolute sign. This equal to 2z because z greater than 0 in this case, in this example, always. Okay, so we have all these terms and we are ready to perform the double integration. Now, here comes the formula, surface area. It's going to be equal to the double integration of the absolute value of f. So in this case we have 2 square root of 2 divided by absolute value of gradient of f dot p. That is 2z. We have to perform this double integration over the domain region R. This R Okay, and as you can see here, this R right here, R is a circle of radius equal to 1. We are working with R that is a circle, so it makes more sense to use polar coordinate. R is circle, so we are going to switch this to polar coordinate, which means that this dA becomes R dr d theta. Okay, let's cancel this for now. Now let's continue. Integration of square root of 2 divided by z r dr d theta, because we switched to the polar coordinate already. Now we have to sweep the radius. Now let's take a look at this region R. I'm not going to make the same mistake as the last example again. So this R sweep from R equal to 0, radius equal to 0, all the way to radius equal to 1. So radius starting from 0 and ends at 1. Alright, and theta, sweep from theta equal to 0 all the way back here. That is 0 to 2 pi. Alright, let's continue this calculation in the previous slide, but don't worry about this mistake. I'm going to fix this before I send it to you. So on your lecture you can just write down just according to the pages. Don't worry about going up here because I made a mistake here. I'm going to fix this in the version that I sent to you. So what do we have here? We have this double integration, radius starting from 0 to 1, and theta starting from 0 to 2 pi. And here we have this square root of 2 divided by z, and r dr d theta. That's what we had before. But we can't continue with this because we still have z right here. Right? We have this z and it's not going to go with r and theta. So let's change it. Here, let's take a look at this. X squared plus y squared is going to be equal to, I'm going to save some space. Okay. This is going to be equal to r squared. Right? X squared plus y squared equal to r squared plus z squared equal to 2, which means that z is going to be equal to 2 minus r squared, square root of that. Right? I'm going to substitute that into the double integration that I have here. So this is going to be equal to double integration 0 to 1, 0 to 2 pi, square root of 2 divided by square root of 2 minus r squared. And it comes from here. Now we have this r dr d theta. Okay, and it looks kind of complicated, so we have to rely on some techniques. So once again, use the first technique you can think of, substitution. So I'm going to make u equal to 2 minus r squared, which means that du by dr equal to minus 2r. Or you can say that dr equal to du divided by minus 2r. Now let's put that in place. 0 to 2 pi, 0 to 1, square root of 2, and now substitution. Inside becomes u, and r is still there. And now dr, we use the new terms, that is equal to du divided by minus 2r. And we still have d theta right here. Okay. Now let's do some cancellation. R and R here. Alright, now I'm gonna take the constant outside, that is minus square root of 2 divided by 2, and we have this double integration 0 to 2 pi 0 to 1 of square root of 2 is already outside, so this just becomes u to the power of minus 1 over 2 du d theta. Okay, let's integrate this with respect to u. So it's going to be equal to minus square root of 2 divided by 2 integration of 0 to 2 pi. Integrate of u with respect to u here should be easy for you by now. This is equal to u to the power of 1 over 2 and divided by 1 over 2, or basically 2 here. And you have to evaluate this at r equal to 0 and r equal to 1. And we still have d theta right here. So two things, 2 here cancel, and we have to put r back into this this expression. So here we have minus square root of 2 integrate of 0 to 2 pi u equal to 2 minus r squared, and then we have this square root, have to evaluate this at 0 and 1 d theta. Alright, 1 goes in, 1 goes in, this becomes square root of 1, so it becomes 1. Minus 0 goes in, this becomes square root of 2. Alright, and integrate this with respect to theta. And you can see that this is just constant. Constant. So you can just take it outside. Alright. Take it outside. This becomes equal to 2 minus square root of 2. Alright, so yeah, minus square root of 2, and this becomes 2. Right, and then inside we still have this integration from 0 to 2 pi with respect to theta, nothing in there, so in the end you get this 2 square root of 2 pi minus 0. So the answer for this is 2 pi 2 minus square root of 2, and that is the area for this piece up here, the top of the sphere. Right, surface, the area of the surface. Okay, so this is it. So this is the last example for the last topic. Alright, so today we covered 2 topics. The first one is Greens Theorem. Greens Theorem is related to the lines integrals. It's just with some extra conditions in order to for us to be able to apply the Greens Theorem. And after that we learn about the surface integrals. The purpose of that is just to find the surface area of something that is in the space, right? Not just on the plane. Okay, and this is the last lecture for this course. And I wish we could meet in the class and say goodbye. Well, we are going to meet on the exam day anyway. I'm going to give you the details about the exam in the line group, about what we need to do in order to prepare for the exam. And I'm going to try to make the exam not too hard, because I know that it's been difficult for everyone. You, me, I have to teach like this, you have to study like this. And sometimes I'm late when it comes to uploading. I'm sorry about that, but just to let you know, it takes a lot of time to teach like this. I have to change all my materials. So yeah, sorry for being late sometime in this situation. All right, just wait for the details about the exam in the line group. So goodbye for now, and good luck for everything. All right, goodbye.